In this video, I will introduce the concept of entanglement distillation, which is a crucial building block of a large-scale quantum internet. We will start with a short motivation. Let us consider a scenario where Alice and Bob are separated by a long distance and they have access to certain experimental setups that allow them to generate long-distance entanglement. Unfortunately, fully entangled states, which are perfectly correlated, are a great idealization and from an experimental perspective almost impossible to create. In general, there can be many reasons for this. For example, their experimental equipment used to generate this long-distance entanglement isn't perfect, or they cannot maintain their quantum systems long enough. Additionally, to overcome the problem of losses over such a long distance, there might be additional repeaters placed between Alice and Bob, which allow them to significantly increase the rate of generating those states. However, such repeater nodes perform then additional imperfect operations, which further decrease the quality of the resulting entanglement between Alice and Bob. Effectively, the quantum correlations become then weaker and completely diluted in a mixture of various other quantum states. This means that the quality of the generated entanglement might be too low for specific applications. For example, two weak correlations would not allow Alice and Bob to generate any shared secret key. Fortunately, Bob, as most physicists, has a lot of experience with alcohol, and he expects that some of the corresponding practical skills could also be applicable in this situation. Specifically, in his previous life, Bob used to work in a distillery. There, a very weak form of alcohol is stored in the massive stills as the ones on the picture. This weak beer is a mixture of pure alcohol, water, and some other substances. For the high-quality whiskey, Bob needed to extract this pure ethanol from everything else. By evaporating alcohol and later condensing it outside of the stills, he was able to separate it from the contamination that shouldn't end up in any high-quality whiskey. It was then possible to separate such alcohol from the water to the desired degree by running multiple rounds of the distillation procedure. Bob then decided to apply such a distillation procedure also to entanglement. In entanglement distillation, Alice and Bob will use multiple copies of weakly entangled states. In this procedure, although each state has some possibly small amount of entanglement, it is possible to combine those copies together and eliminate the contamination by extracting only the entangled part, so that at the end smaller number of more strongly entangled states can be extracted. Guided by his experience in the whiskey distillery, Bob knows that for realistic procedures, a single run of such an entanglement distillation would in most cases not be enough, but repeated procedure will be necessary. Also, similarly to alcohol distillation, where the total amount of alcohol cannot be increased, the local operations and classical communication used by Alice and Bob allowed them for concentrating existing entanglement into a smaller number of copies without increasing the total amount of entanglement. The main goal of such an entanglement distillation procedure is to increase the quality of the resulting entanglement as much as possible. Here we can, for example, use fidelity as a measure of closeness of the resulting state to the maximally entangled one. However, any practical entanglement distillation procedure is normally probabilistic, which means that there is only a finite probability that the resulting state that Alice and Bob obtain is more entangled than the input copies. These procedures are fortunately heralded, which means that the devices of Alice and Bob raise flags that tell them whether the procedure has succeeded or not, and therefore whether they should keep or discard the resulting state. As one could expect, there is a trade-off between the two effects. In particular, if one designs a procedure that allows us to greatly improve the fidelity, such procedure will generally succeed with very small probability. Conversely, if one wants to focus on a procedure that succeeds with high probability, the corresponding gain in fidelity will in general be small.